Hi, good afternoon, everyone. I'm really sorry. Yes, on Wednesday we had a technical issue. As the result, the whole lecture did not have sound. I saw that to remake a video, but given the just kind of short time frame between Wednesday and Friday, I saw that if I remake the video, you might not have enough time to get ready because a lot of people rewatch the playback instead of the live streaming. So unfortunately, today I will essentially redo the Wednesday lecture so that right now we are kind of about 1 week behind the schedule, but we will figure out a way to catch up at some point because either during the winter break or one of the break week. So don't worry. So today, like I said, is still lecture 10, supposedly on Wednesday, but we will hopefully now voice is good. I do see my microphone is picking up the sound for the streaming feed. So today we will actually talk about something really important, and that is we will introduce the concept of subtraction over natural numbers. You may become curious, subtraction? I haven't known this for years, at least since the first grade. And that might be true, but what you don't realize that when you learn subtraction, you never get a chance to ask, excuse me, what is exact subtraction. As a matter of fact, you probably never asked what is addition in the first place. But as now you should have known, the concept of addition is not that trivial. Math is not just about giving you some very mechanical things to memorize. So everybody understand how things like 5 plus 3 equals to 8 or 8 minus 3 equals to 5. Everybody understand how that works. But to truly understand the mathematical meaning of those things might not be trivial. In the future, when you learn higher math in college, you may study something called abstract algebra. Of course, you have not even learned algebra yet. But just as a heads up, when you learn abstract algebra, you will see that we really care about the addition and multiplication operations. That's because subtraction can actually be defined via addition. In other words, subtraction is actually just a different statement of addition. And similarly, division can be defined through multiplication. Or division is just another way of stating multiplication. And those are very important concepts in abstract algebra, which kind of put what we learn in those kind of basic arithmetic into a more general framework. So abstract algebra will include everything we learn with numbers, natural numbers, and then something more abstract. But for now, today's focus will be really help you to understand what truly is subtraction and how we properly define subtraction. Remember, so far, we have took pain to review what addition is and then introduce some really new concept for you to understand fundamentally what numbers are, what the addition operation is. Recall that we took a lot of new concepts and new definitions to get something that you assume you had already known for a long time. And subtraction actually is just one step further, but we better start with reviewing what we have already learned with addition and natural numbers. Okay, so subtraction, what is it? Why need it? Well, you see a tiny mystery symbol right here, right? We will reveal what it is. Okay, let's first consider a familiar problem that we have already studied. When we study addition, we look at this problem. If we have 5 apples and 3 bananas, how many fruits in total we have? We know this is 5 plus 3, but what is exactly 5 plus 3? Well, we define this through a counting process. So 5 plus 3 is nothing but you start at 5 and then count forward 3 times. 5 to 6, 6 to 7, and 7 to 8. So addition is just fundamentally repeated counting forward. We know that. Okay. So now with this problem, we can consider a similar problem. Now we just replace the 3 bananas with 3 apples and then see how that works. So it doesn't matter whether the last 3 fruits are bananas or apples. Let's just assume that we only has apples. Of course, 5 apples plus 3 apples give us 8 apples because we count from 5 3 times, get 8. Now what if we remove the 3 apples, which demonstrated in this dashed rectangle shape? What if we remove the 3 apples that we just added from what we know as the total 8 apples? We know we have, the question is now, we know we have 8 apples in total and we remove 3 from them. What shall we get? Remember, we don't have subtraction defined yet. For now, the only thing we know about numbers and arithmetic is just how the natural numbers are defined and what is exactly is addition. And we do know multiplications also, but we don't know anything about subtraction. We don't even know what the concept of subtraction is. But now we face this problem. We have 8 apples. We want to remove 3 from those 8. So we know 2 numbers. One is 8, one is 3. We want to get a new kind of result. We expect that to be a number, right? To be a natural number. So we know we need to do something on those 2 numbers, 8 and 3, and get a result. Of course, we know the result should be 5, but at this time, we don't know how to get that 5. That's the question. We have not defined what subtraction means yet. But intuitively, you can think about, we need an operation. This operation will operate on the 2 given numbers. One is 8, one is 3, and the result should be, not surprisingly, 5, right? So we just know we need an operation to get this 5 based on the inputs, which are 8 and 3. So we temporarily represent this operation like this. We have 8, we have 3, we have something that represents an operation and will give us a result. We expect that to be 5, but we are not sure yet. We just expect this result should be 5. Okay, that's our first step. We just abstract this idea into something like this. It looks a little bit mathematical, but we really don't like the simple thing, right? This looks awkward. So why don't we just replace it with a much simpler symbol? And better yet, we better use what we had already known about subtracting. So we will just use the subtraction symbol to replace this bizarre mystery symbol. So we just write this as an undefined operation. We do use the subtraction symbol to represent this operation so that it will be actually consistent with what we had already learned. But remember, at this time, we don't know what this is or what this means. We just know this is an operation that we want to have and which hopefully will give us the expected result, which is 5. That's where we are. So how do we define this operation? Well, it helps if we can actually first review how we get addition, right? This should be very familiar to you guys now, but it always helps to review. So that's what we had. 5 apples, 3 bananas. We counted from 5 3 times. That's how we define it mathematically. 5 plus 3 defined as increment on 5, then increment again, then increment again. Now we know that's just 5 plus 1 plus 1 plus 1. Okay, so on the number line, it looks like this. We start at 5, increment, 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 and that gives us 8. If that's the case, what is exactly this 8 minus 3 thing should be? We're essentially subtracting or removing 3 apples from the 8 apples. What do we expect to get? Must be something here, right? If we count it, of course, we will be able to find this will give us 5. We counted, we literally counted 1, 2, 3, 4, 5. That's what is left after we remove the 3 apples. So that really motivates us to rewrite this last expression into something like this. We are trying to get a result, right? And we can represent that result with just a question mark. If that's what we have remaining, then we can reverse this process. We can put the 3 apples that were removed back to what is remaining, then restore the original addition, right? It's just the same thing. You remove it first, then you put it back, then you get back to where you are. So, if that's the case, this question mark represents what we should have after removing the 3 apples. We can rewrite the addition operation like this. So that means that those last 2 expressions are essentially the same thing. They mean exactly the same thing. We just write them in different ways. One is with this new, not yet defined operation called subtraction. We want to define something for this 8 minus 3. On the other hand, we understand whatever result we have, this result should make the last expression make sense for that. Whatever this number is, we plus 3 from this number should give us 8. So clearly, subtraction is nothing but a restatement of addition, just in an inverse way. All right, that's very important to understand. So subtraction can actually be either defined or just say it's a restatement of addition. by the way, for those of you who are really smart and advanced, you should recognize that the very last expression is essentially exactly the same thing as what we call an equation. That is algebra. So if we replace this question mark with a symbol, let's just say x, right now we have this last expression written like this. But a symbol is just symbol. It can be any symbol, right? So if we replace this question mark with a symbol, say a letter, call it x, then we can write this essentially the same thing. And that is what we call an equation. And this is 100% algebra. So effectively, when you learn subtraction in the first grade, you have already learned some algebra, because essentially your idea of subtraction was based on this observation. If I need to subtract 3 from A, essentially we are looking at this problem. What can make this addition make sense of it? That's actually algebra. But the important takeaway here is that subtraction is actually deducted from addition. But luckily, we have already spent a lot of time to rigorously define what addition really means. So now we are in a great position to understand what subtraction should mean. Okay, so now let's take a look at a slightly off the track issue. Since we are removing 3 apples from a total of 8, if we start with aligning the apples on the line, 8 apples in a row, does it matter from which end we remove the 3 apples? It should not, right? That's just common sense. So if we remove the 3 apples from the beginning row and the end of this row, what happens? And what kind of difference did we just make? Well, if we remove these 3 apples from the end, we should write this addition equation, which with the question mark in this way. Question mark plus 3 equals to 8, because we count that the last 3 is always the things being added. So if we remove the 3 apples from the beginning of the row, how shall we change or modify the last expression? It must look something different. It must be something like this, right? Because now the 3 apples we remove at the beginning of the row, it becomes, the question mark becomes what we want added to 3. This is just the reason we are writing those 2 additions in such different ways, just make them consistent with our definition what addition should be. Remember, in addition, the first number is the base number you start with, and the second number being added to the first number is kind of the number of increments or counting forward steps you should perform. So if this is the way, the right-hand side, which we know is 5, it's something that we need to figure out, then it should be the question mark in this equation. So just want to know that just essentially the 2 things are the same. And the very reason we can do this is because commutative property. In other words, commutative property essentially is saying that when we do subtraction, it doesn't matter from which end we can remove the 3 apples. From the beginning or from the end, the same thing. Because the commutative property just means exactly that. Okay? So this is kind of just a digression, but our focus is first, on the first one. When we subtract 3 minus 8 equals to this question mark, we are essential to figure out what question mark number should be to satisfy this question mark plus 3 must be 8. Okay, so now that's our motivation for how to define the subtraction. So at this point, we know subtraction seems to be just some inverse of addition. Okay, so it's an inverse of addition. Just still from a logical perspective, that should be the way it is. But how do we rigorously define subtraction, just like what we did for addition? Well, why don't we just go back to the addition principle? So 5 plus 3 equals to 8 on the number line is from 5 increment, increment, increment. If this is inverse, what will happen? We remove 3 from 8. Then it must be on this number line, the increment operation should get reversed. So it will be from 8 to reduce to 1 or decrement. That will give us or should give us 7. And we do this 3 times. So decrement, decrement, decrement. So that we can go back from 8 to 5. And that's exactly what we should define this whole thing. And we should define subtraction just analogous to how we define addition, but we counting backwards. The counting is not forward, but backwards, and use a decrement operation on the natural numbers. So that gave us something like this. Okay, on the number line, we started at 8. That's what we know. And now we remove 3. We have to decrement, decrement, decrement 3 times. Okay, so what is exactly decrement operation here? Well, in math, we have to do everything rigorously, just not by English. Say, oh, decrement is the opposite of increment. It's just the inverse. What is exactly this? I don't know. It's just opposite. No, we cannot do that in math. We have to give it a rigorous definition. But we will see that in a moment. With this understanding, subtraction should be fairly understood as an inverse of addition. So let's first review how we actually define addition rigorously. And that involves how the natural numbers were defined in the first place, right? Remember, in order to define the natural numbers, we need 2 critical things. Actually, and then 2 also important but kind of auxiliary things. So we need a set of 4 axioms. I have to emphasize that actually this is what we call the piano axiom system. We actually need 1 more axiom, which is called mathematical induction, but we don't want to introduce that at this time. So we merely stay with those 4 axioms. And the first one, the second one are the most important. The first one says that we all agree 0 is a natural number, which in this context represents the initial state of a counting process. And then we all agree there exists an increment operation. It's the same increment operation that applies to any natural numbers. And whenever we run this increment operation on a given natural number, we get a new natural number, which is the next in counting natural number to the current natural numbers. In other words, whenever we have a current given natural number, we run the operation, increment operation on that, we get a new increment natural numbers, which is the next one to the current one. Okay, so this is the important, actually the most critical part of this so-called Peano's axiom system, because this very increment operation give us what? Give us 1. Because we run it before anything, we only have one natural number, that is 0. But with 0 and this increment, we will immediately get 1. And once we get 1, you can imagine on the number line, we say that on the number line we can randomly choose an arbitrary number, arbitrary point to be number 0. We can similarly arbitrarily choose another point as 1, but this one has to be on the right of 0. And the reason of being on the right is just convention. The convention is that the numbers will just go up toward the right-hand side. It could be defined in the opposite way, but we don't do that. So other than 1 has to be on the right of 0, 1 can be really arbitrarily chosen. But once you have chosen both 0 and 1, your freedom comes to an end. You cannot arbitrarily choose other point to represent the natural number. Instead, you have to use the length between 0 and 1 as a so-called unitlength to define all those natural numbers on the number line. And that is consistent with how we define with the natural numbers. 1 is next one to 0, and the next one to 1 is 2, the next one to 2 is 3, and so on. We just keep using this increment operation to recursively define all the natural numbers. And with that, we were able to define addition. Now, we can see that we will be free to reuse those definitions to define decrement and the subtraction operation over natural numbers. Okay? So now we are tasked with this question. We have 8 apples. We remove 3, or in the abstract, we have 8. We want to subtract 3. What shall we get? We know whatever we get, it should meet the inverse addition operation, which is this number plus 3 should give us back 8. Okay, and if that's the case, on the number line we do decrement, 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 and this new operation subtraction should give us 5. Otherwise, there's something wrong with the definition. So, based on what we just saw, how we define the natural numbers and the increment operation, which eventually lead us to define addition, we can feel that everything just the opposite. We just take the opposite to get the inverse. Therefore, the way of defining subtraction for our current needs is just to solve a problem like a minus 3 equals to what? For this kind of problem, it should be fairly easy. And that's how we are going to do next. Okay, so first, I hope you can see well. It's a little bit small on the screen, but hopefully you are using a quite big monitor, so not just iPad. So we first define what is the decrement operation over natural numbers. Okay, this is very important. For now, our decrement operation, look carefully, we use a little case d, just like we use a little case increment. We will see next week when we study negative integers, we will introduce a similar concept but with a capitalized d. or in the case of increment, we use a capitalized I to expand the definition of such operation. But for now, very important to understand this decrement operation, it's on natural numbers with some caveat, and that is, how do we define this decrement operation? We say for any natural number m, right? Could be 0, could be 2, could be 100, could be 1 million. A decrement operation, look very carefully. The definition is not on m, but on m plus 1, which, as we know now, m plus 1 is just the next natural number in counting to m. Just m's next number. It's just m plus 1. That's from the counting perspective. But once we have defined addition through counting, we know it's the same thing as m plus 1. So look very carefully. Our decrement operation is not based on any natural number m, but on the next number to m, which is m plus 1. So what is a decrement m plus 1? Well, we just define it to be m. Isn't that obvious? Yeah, m plus 1, a decrement by 1 must be m. Of course, this is very straightforward, but there's a huge caveat here why we took such an indirect route. Say, given a number m, we define it on m plus 1. This is to prevent the case where we may have a problem if we define through m. If the decrement is on m, what could be the potential problem? We don't know what is decrement on 0. Remember, if we look at how the increment was defined, we start from 0. That's why we have 0 as the initial number on counting. We start from 0, increment 1, 2, 3. When we do the decrement, we say from 8 to 7, 7 to 6, all the way 3 to 2, 2 to 1, 1 to 0. Then what? Our decrement operation cannot be defined on 0 because there's no previous number. That's actually a reason, one of the reasons why number 3, axiom number 3 is needed. You may have overlooked the significance of rows, but we mentioned they exist to prevent counting loops. And one special counting loop is that if you count, say, 1, let's use red, which would be better, I think. If you have 1, 2, 3, 4, of course, you start from 0. Now, what if I tell you it count forward and the next number is 0? Well, if that's the case, if this is indeed the case, we can say decrement 0 should be 4, right? And this is a loop. From this point on, you will get 1, 2, 3, 4, and 0 again. We don't want this to happen. We don't want to have a loop in our natural numbers. So therefore, we need axiom number 3 in order to prevent any counting loop that go back, wrap around, go to 0. If that actually can happen, we have no difficulty define decrement 0 to 4, which of course is kind of ridiculous. But for those really advanced, you can see that in what we call the modular arithmetic, we could have things like this. Okay, so this would be a mod 5 arithmetic. And in that case, 0 equals -1 equals to 4. Okay, so that's just a different issue. So now with axiom number 3, we know no natural numbers can have 0 as its next in counting natural numbers. Therefore, no number plus 1 would be 0. And as the result, decrement 0 does not make sense. Okay? So we prevent this from our definition in the first place. Decrement of 0 is ill-defined. We cannot do that. And we will see what the practical meaning of this is. So once we have understood this, now to understand the definition of this decrement operation is very clear. Because we want to prevent the awkward case, we want decrement on 0. So our decrement operation is always based on m plus 1. So the smallest case would be m is 0, right? For any natural numbers m, the smallest of m is 0, and therefore the smallest of m plus 1 is 1. It cannot be 0. So our decrement operation now is well defined. We don't have anything to worry about because we are defining decrement on m plus 1 rather than m. That's why this is the case. So now once we have this decrement operation, which you can safely tell is just exactly the inverse of the increment. Okay? Except that with increment, you can start with 0, you can go forward forever. But with decrement, you come back. Once you hit 0, you're blocked. You cannot do anything on 0 for decrement. Okay, that's the only difference. Otherwise, decrement and increment, they are just perfect inverse of each other. All right? So, with this, now we are ready to define what subtraction over natural numbers is. Okay. So now, with this visual aid, which it simply says that the decrement operation on a natural number which is at least 1, cannot be 0, at least 1, decrement on this natural number, it's just its previous. But we don't have to worry about the previous because our definition is already m plus 1 rather than m. We always know there is a m right there for our use. That's exactly why in this definition, we start with m, but decrement on m plus 1. So this is the visual explanation. You go down until you hit 0. And with this, subtraction of natural numbers. So that m and n be any natural numbers, except there's a constraint where either m is to the right of n on the number line, if you know what it means by bigger than or smaller than, which we have not just formally rigorously discussed about, that introduced the concept a number is larger than the other number. But this is a preview of that. If m is to the right of n, meaning that m is larger than n, or m and n could be same number. So either m is to the right of n on the number line, or m is the same as n. We allow those cases. So the only cases that has been excluded is m to the left of n, meaning we know that means m is smaller than n, but because we have not officially talked about what it means by smaller, which is exactly the definition here. So we have not talked about that, so we just say m either to the right of n or m is the same as n. Whenever this constraint is satisfied for any two natural numbers m and n, Then the subtraction operation, this subtraction symbol operation over m and n, and written as m minus n, which you should familiar with. Remember, m is the larger one or equal to n. So m is either greater than or equal to m. In this case, this subtraction operation is defined in this way. We define m minus 1, just like how we did m plus 1, right? This is essentially the decrement operation we talk about. We have already taken care that m will not be 0. If m be 0, m minus 1 is not defined, but m minus 0 will be defined in the second one. We'll see that shortly. But for m minus 1, for this purpose, m cannot be 0, or m just cannot be 0. Okay? So, decrement m, that's what we define just in the immediate above definition. So we define this is decrement essentially is m minus 1. m minus 1 is decrement. The same thing. The only constraint is that m should not be 0, should be at least 1. That's the only concern. And what we have that, what is m minus n? Subtracting n, it's just that we from m, we do this decrement n times. You can see that this definition is just kind of mirror image of how we define addition, right? And that is exactly what it should be. So m minus n is just performing this subtracting 1 n times. But remember, n could be 0 here. If n is 0, this simply means nothing. You don't do anything. M subtracting 0 is just m itself, because it says perform this minus 1 n times. N is 0, so you don't do anything. You don't do anything, the number won't change. So it must be m. Okay, so that is also well defined. So m subtracting 0 is well defined. Okay. Well, with this, now we know our definition of the subtracting what it really is. So we know we have this one. So defining subtraction based on current needs would be really easy. Just we introduce the subtraction as decrement and repeated decrement. But we still face a fundamental constraint. The number being subtracted must be no greater than the number being subtracted from. Okay? What that really means in very advanced language is that the natural numbers are not close on subtraction. What that truly means is that we are faced with this constraint. The first number need to be at least as large as the second number. But we don't have this constraint with addition, did we? No, we don't. Because with addition, any two natural numbers, we can add them up. But with addition, this fundamental constraint, the first number need to be either greater than or equal to the second number, is so important. And this is true before you studied negative numbers, right? I don't know how many of you have already studied negative numbers, but I'm pretty sure in grade 1 or grade 2, when you do subtraction, you were prohibited from subtracting a larger number from a smaller number. Okay, so now what this means is that we have to answer this question. What if the second number is larger than the first number? Well, you may ask, does this even make sense? I only have 8 apples. You want to remove 13 apples from my collection of apples? How could this be possible? Well, ask Uncle Sam. Because the US government can always spend more money than what it has, right? I'm not joking. You know how big the natural debt is? I'm not joking. So, in reality, this can happen. It just doesn't happen in some really physical object sense that you only have 8 apples, you want to give others 13 out of 8. That would be impossible. But what you can do is that you borrow 5 apples from your brothers, sisters, or even from your friend. You temporarily have 13 apples, and you can give all of them away. But what happens is that at the end, you have 0 apples left, and you just borrowed 5 apples from your sibling or friend, so you owe them 5 apples. You need to give them back 5 apples. So make a better example. Let's just do a little bit mimicking of the US government. Let's just say we have a great company called Child Credit Bureau kindly gave every kid of 10 years age or older a credit of $100. Everybody knows what a credit is, right? You can buy on credit a credit card. So a credit card allows you to buy something without first having the money. You can buy that. The only thing is that you have to pay back to the credit company. And usually if it's interest free, you don't need to do anything. They can make money from somewhere else by the transaction, for example. But it's not something that allows you to spend money without any limit. It's just a temporary convenience. You can borrow money, or essentially in this case, using the credit to buy things that you currently do not have cash to buy. But within certain time, say 30 days, you have to pay that back. If you don't, you will be charged interest. You will have to pay a lot more. So everybody should have a good, sound, just financial habit, just paying your credit card on time and pay it in full so that you don't incur an interest charge. But back to our question. Let's just say you want to buy a good, just an Xbox remote. It costs $13, but your grandpa just gave you $8 in cash as an initial deposit into your credit card account. So you have 100 of credit. You also have $8 in cash, which was given by your grandpa. You can actually, in theory, at maximum, you can afford to buy something 108. But let's just say you don't want to spend just irresponsibly like that. You do want to buy this remote, which is $13. So in this case, you can subtract 13 from the 8. And what is net result? Of course, we know that is -5, which is exactly your remaining balance on your credit card. You owe the credit card company $5. And essentially you have a debt, and you have to pay that back pretty soon. Otherwise, you will be charged interest. So 8 minus 13, something like this can actually happen in the real world. It's not some joke or something just kind of academic that had no physical meaning. No, it has very real physical meaning. But how can we do this? We cannot do anything about it without subtraction, right? We were prohibited from doing this in the first place. Why? Because our subtraction definition, this operation only works for a limited case of natural numbers. To be more specific, the first number cannot be larger than the second number. That's our agreement when we define this subtraction operation in the first place. And fundamentally, it's because of that on the number line, we only define half of the number line. We only define everything to the right of 0. And That's what we call natural numbers. In other words, with subtraction, it seems that there's a fundamental roadblock which we cannot possibly overcome with everything we have defined so far. We have defined natural numbers, addition, multiplication, which is repeated addition. Now we have defined subtraction, but our subtraction is not perfect. We cannot just give the subtraction operation any two arbitrary numbers like 8 first and 13 second. That doesn't make sense within this system. What can we do? What can we do to solve this problem? And that's very important because now you are at a junction where what we will do is to generalize something that we are comfortable with into something we don't even know yet. Right now, we are comfortable with working with natural numbers, addition, and subtraction, but the subtraction is limited to about half of the case. Literally, the first number should be bigger than or equal to the second number. But in reality, that doesn't have to be the case. The second number can be bigger than the first number. What can we do? That represents about 50% of the case. So we have to do something beyond what we have. And that is expanding our number system from natural numbers, which we know 0, 1, 2, 3, to integers. And what is the difference between integers and the natural numbers? Those are negative numbers. And I'm sure at the beginning of this course, when we introduced the number line for the very first time, we gave you how it looks like. We have all those negative numbers to the left of 0. So this is a 0, this is 1, this is 2, this is 3, and so on. But we completely left everything left to 0 blank. We don't have anything there. Now, we need to expand our natural number system into the left-hand side of 0 on the number line. And the motivation here is to answer questions like 8 subtracting 13, what is that? What do you think? What is that? Well, when we subtracted 3 from A, we just counted from A 3 times. So this is 5. This is, if I expand this a little bit longer, so further to the right, 6, 7, 8. If we subtract this 3, just count 3 times to 5, we don't see why this cannot continue to subtract one more, and 13 is bigger than 8. That means that we want to count leftward, or just backward, 13 times, but we're only allowed to do this 8 times, and once we hit 0, we know there are 5 more remaining decrement we want to perform starting at 0. We want to go deep into the left of 0 on the number line. We want to do 5 more times, right? And what are rows? Of course, it's quite easy to see. In this case, every time we decrement 1, that decrement should have exactly the same meaning even when we are operating in the negative or the left-hand side of 0 or negative net territory on the number line, all those decrement should be exactly as those decrement we were doing for positive numbers or natural numbers. Even we have not even defined what rows are, which we will know will be -1, -2, -3, -4, and finally the last one give us -5. But more importantly, we want to understand that this decrement operation, once we go into the negative part of the number line, should be actually consistent what we already had. That is, on this part, all the decrement on this part, rows decrement should mean exactly the same thing. But what do we mean by exactly? We don't even know what those numbers are. We have not even defined those numbers. How can we possibly know what the decrement operation means? Well, that's exactly a challenge. So we will see in the next lecture how we can, based on what we have already studied and carefully define about increment operation, which give us all the natural numbers and the counting gave us addition, and addition gave us a multiplication. Now with today's material, we just define, we don't need any actual axiom, we just define a decrement operation over natural numbers. But this decrement operation is not gonna be sufficient for us to get negative numbers, because you cannot get what you don't from what you don't have, right? We don't have any increment operation on the negative integers. Our increment operation always starts from 0. So maybe as an exercise, you should think about this problem. But before really putting any thought on this problem, think about exactly what we have been doing. We just try to carefully to build from the ground up what numbers are, what those arithmetical operations mean, and now we want to expand our new coined operation, which is subtraction. We want to make it perfect, or at least complete, in the sense that we want to allow any two natural numbers, it doesn't matter which one is bigger, we want this operation to make sense. And we preview, understand that will give us negative numbers. But now the challenge is that we want to properly define everything. So based on what we have with the natural numbers, increment, and today's decrement, how can we achieve that goal? We will discuss this next time. Okay? I should give you back the solutions on row 30 word problem with those two quantities, the three multiple relationships. So we already discussed some of the most challenging problem from row 30 problem. I should give you the solution back, and I will give you some additional homework. So today, again, I apologize for the technical difficulty of yesterday, essentially, not yesterday, Wednesday. So we are redoing Wednesday's lecture, and so everything otherwise should be fine. So I'll see you on next Wednesday. Thank you. Bye.